everyone, welcome back to the channel. My name's Rob. So, are you looking for the most organized design when it comes to multiple ISP connections? Well, if that's the case, then you have come to the right place. I won't lie, the configuration is a little bit complex at first. We'll be using VRFs and multi-protocol BGP, so that way we can leak routes between VRFs. But once that's done, you'll be left with one clean, flexible, and scalable setup. So with that being said, let's jump right over to GNS3 and I'll show you what this is all about. If we look over here at the topology, we have two ISPs, and then they all terminate into R1. So I'm kind of faking the internet up here. So these clouds in GNS3 actually terminate into my actual physical computer network. So we're essentially just using virtual routers right here and performing NAT on the ISP side. So that way it looks like the traffic coming from these ISPs is directly connected into these subnets. So they both terminate into R1. This is actually going to be the center of the configuration for the entire video, actually. So I haven't configured anything on R1 yet except for the host name. So if I issue the show run command, everything is going to be at its defaults. Okay? And then everything southbound of this router is just layer 2. So we have a layer 2 switch here with the PC hanging off of it. And this is the PC that we're going to be using at the end to test to make sure things work. So if we look at these subnets, they are all RFC 1918 private addresses. Again, that's because, like I just mentioned, we're faking the internet, so it doesn't really matter for this example. But we're looking at 172.16.1.0/24 for ISP1, so it's interface that's facing us. And for ISP2, it is on the 10.0.0.0/24 network. So we have the .1 over here and then .1 over here. So ISP1 will have the IP address of 172.16.1.1. Then over here, 10.0.0.1. On the LAN side of our router, we are on the 192.168.1.0/24 subnet with the .1 up here on R1. Okay, so we are going to configure 3 VRFs. We're going to have a WAN 1, a WAN 2, and a LAN VRF. After we create the VRFs, we're going to leak routes between ISP1 in the LAN, and then vice versa, and then ISP2 in the LAN, and vice versa. So again, like I stated at the beginning of the video, this kind of cleans up the routing tables a little bit because you're not lumping everything into the global routing table, and you're essentially, by using VRFs, you are breaking the router up into separate virtual routers. So in this case, we're looking at 3 virtual routers, and we have that more granular control over what routes are populated where. We're going to configure those VRFs, BGP, and then we're also going to move to the IPSLA configuration so we can have failover, as well as NAT and everything like that. So let's pop open R1. And we will start with the VRF configuration. So I'm going to have 3 VRFs, WAN 1, WAN 2, and LAN. So I'll start by saying VRF definition WAN 1, address family IPv4, and we will give it the route distinguisher of 1, 1. So we're going to keep this real simple. And so I don't have to go back into the VRF configuration. I'm going to add the route target export and import commands right now. And I can do that because I already know I'm going to assign WAN to a route distinguisher of 2.2, and the LAN I'm going to assign a route distinguisher of 3.3. So when I say route target export 1.1, what I'm essentially saying is that when I fire up multi-protocol BGP, I'm allowing routes to be exported into multi-protocol BGP, so that way I can import them into other VRFs. So we are exporting our own routes since we are 1.1, and then I want to import 3.3, which again I haven't configured it yet, but when I do, the LAN VRF will have the route distinguisher 3.3. So I'll say route target import 3.3. Okay, and then VRF definition WAN 2, address family IPv4, route distinguisher 2.2, route target export 2.2, route target import 3.3. So again, we are going to be exporting our own routes into multi-protocol BGP, as well as importing routes from the LAN VRF. Okay, last but not least, VRF definition LAN, address family IPv4, route distinguisher 3.3, route target export 3.3, and then since we want to import into the LAN VRF routes from both ISP1 and ISP2, we're going to say route target import 1.1 and 2.2. Okay, so the VRFs have been configured. The next thing I'm going to do is move to the individual interfaces and apply those VRFs to the corresponding interfaces. So we'll start with gig 0 for ISP1, move over to gig 01 for ISP2, and then gig 07 for the LAN. So I'll say interface gig 00, VRF forwarding WAN 1. No shut. Interface gig 01, VRF forwarding WAN 2, no shutdown, and then interface gig 07, VRF forwarding LAN, no shutdown. Okay, so let's work our way back around, starting with gig 00 and start assigning IP addresses. So we'll go back to gig 00, and the IP address will be, so like I mentioned, since this is this segment right here is 172.16.1.0/24, and this is the .1, we will say on gig 00 the IP address is 172.16.1.2. And in case anybody out there is wondering why I'm not using /30s for these, which I can completely understand if that's what you're thinking, it's because this was, when I set this up, I was mainly trying to simulate an ISP, like a residential ISP like Comcast or Spectrum, where they just throw you on a, a big giant subnet, and this is not actually meant to be a point-to-point link like if you were running BGP with these providers. Okay, so IP address 172.16.1.2/24 mask. Gig 01, IP address 10.0.0.2/24 mask. Oh, we already did a no shutdown. Interface gig 07 will be 192.168.1.1. Okay, so let's go ahead and issue the do show IP route command. And we have nothing. Nothing at all, because this is the global routing table. We're using VRFs for all of our interfaces. There's going to be nothing in there. So now we have this more, like I was mentioning, this granular control over, again, like what routes we want to leak between VRFs, but also what routing table we want to see. So we can say do show IP route WAN 1. I do this every time and then get stuck in this. And then when Control-Shift-6 doesn't work, okay, it looks like it did that time. But I know some of you watching are like, you know what? when you see translating whatever and the Control-Shift-6 doesn't work, you might as well just take a coffee break. So we'll say do show IP route VRF WAN 1. And we see that we have routes in the WAN 1 VRF that only pertain to ISP 1. So we have a directly connected route. So we have the 172.16.1.0/24 subnet, and then local will be that 172.16.1.2, the IP address that we just assigned to gig 00. And it'll be the same for WAN 2, and the same for LAN. We only see in these VRFs what is directly connected, what are directly connected interfaces that are part of these individual VRFs. So the next step is to start leaking routes between VRFs. So we already configured the VRFs themselves. We configured the route distinguisher and the route target import and export commands. We configured the interfaces with what VRF they belong to, as well as an IP address. So now, if we go into router configuration mode, so we'll say router BGP, and we'll just say 1 for the autonomous system number, since it doesn't really matter, since this is a lab. And we'll say BGP router ID, all 1s. And then address family, IPv4, VRF, WAN 1. And this is where we're going to redistribute what we want between VRFs. So we will say we just want to redistribute everything that is a connected route. So we'll say redistribute connected. And then we're also going to have a static route for our default pointing to this router on ISP1. We also want that to be visible in the LAN VRF. So we also want to redistribute static along with the default information originate command. Now, really quick, and I don't want to go off on a sidetrack, but let me just pull something up really quick for anybody that's curious. I thought that I would throw this in here really quick because there are multiple ways to redistribute a default route in BGP. There are 3 of them, in fact, and I made notes of this. So let me just pop open my documents, go into Cisco, BGP default route originate. So we use the default information originate command, and the conditions are that the default route exists in the routing table, plus you have to redistribute static. So you see that the default route doesn't exist yet because we haven't created it, but it's going to. But along with redistribute static and default information originate, it will originate that default route. The 2 other ones are you can say network and then all 0s. And with this is kind of like saying default information originate. The default route still needs to exist in the routing table in order for that to work. And you could also go, if it was traditional BGP peering, obviously we're using BGP in this example for leaking routes between VRFs, but you could issue the neighbor, and then whatever the neighbor was, you know, blah, 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 and then default originate after that. And that will originate the default route unconditionally. So with the neighbor, you know, say 192.168.1.10 default originate, the default route does not have to be in the routing table for it to originate the default route. So I just, I didn't mean to become sidetracked. I just wanted to throw that out there for anybody that's curious, and maybe I can save them some time down the road in figuring out the different ways to redistribute a default route in BGP. Okay, so back to this. We have redistribute connected. You want to throw everything into this that's connected and everything that's a static, which is mainly for the purpose of that default route. So we're going to hop over to WAN 2, and we're going to say the same thing. Redistribute connected, redistribute static. And you know what? I'm actually getting a little bit ahead of myself right now. I'm going to have to go back in here and change this because I'm going to have to add a metric, because the idea when we're done is that ISP1 will be primary, ISP2 will be secondary, so we're going to be performing route failover. By just saying redistribute static under both of these address families for WAN 1 and WAN 2, they're just going to fight over each other. And since there's no equal cost multipathing by default in BGP, even though I could change that by the maximum paths command, by default it's going to pick one of them. And when we redistribute things, the metric is lost. So even when we configure the default route and we put a higher metric, or should I say a higher administrative distance on ISP2, so that way ISP1 will be primary, and then of course we're going to link it to a tracking object. Once it's redistributed into multi-protocol BGP, that metric is lost, so we need to set that in here. So we're going to be revisiting this, and we're going to be setting a metric on these statics when all is said and done. But as of right now, I'm going to leave it as it is, and then just move on to configuring the LAN VRF. So with the LAN, we're just redistributing connected. Okay, so let's exit back out to global config and issue the do show IP route VRF, and we'll say WAN 1. Do you see the difference from when we previously issued this command? You should notice that we now have a BGP route that is directly connected on gig 07. So we now have the 192.168.1.0/24 network visible in the WAN 1 VRF. So when traffic is coming in from ISP1, it knows how to get there, so we just leak that between the LAN VRF into the WAN 1 VRF. And the same will be true for WAN 2. See, we have that BGP route there. And the same will also be true of the LAN VRF. So we should see two routes for both providers. Now we don't see a default route yet or anything because we haven't configured that yet, but that is what we're going to be moving to next. So the next step is going to be configuring. First, I think I want to do a tracking or an IPSLA probe and then link to a tracking object, so that way we can set ourselves up for route failover. Then we'll create those default routes, change the metric of multi-protocol BGP, and configure NAT. So let's start with, actually, I don't want to waste too much time talking about it for anybody that might already understand this, but for those of you that don't, let me just give you a very brief overview. So we have ISP1, ISP2. ISP1 is going to be primary, ISP2 will be secondary. The way we accomplish this with route failover is essentially tracking the status of the primary ISP. Since we're not running BGP with the provider, there's no dynamic routing protocol running here. The only way to find out if they're down or not is to send like a sonar over the wire and see if we have reachability or not. So you want to pick a well-known IP address on the internet, so say something like Google, or a typical one is Google's 8.8.8.8 DNS servers. You might want to track 2, so that way you don't erroneously fail over if that service happened to be unavailable for whatever reason. But essentially, you set up your IP SLA monitor to ping that well-known service on the internet, and then tie it to a tracking object. You tie the default route to that tracking object. So if that tracking object goes down, the route will be pulled from the routing table, and then we're going to have a secondary default route with a higher administrative distance that will then be installed in the routing table once that one is pulled for the primary, and then that will essentially guide all traffic through ISP2. So that is what we're doing right now. We're going to configure the IP SLA monitor, schedule it, configure the tracking object, default routes, and then we'll move on to NAT. So we'll start by saying IP SLA1, ICMP echo, and we'll just use 8.8.8.8. Now, like I just mentioned, in production, you probably want to track more than one well-known IP address. So again, it would be very unlikely, but once we tie this to the default route, and this is going to be what's keeping ISP1 alive. So if for whatever reason 8.8.8.8 or whatever IP address you choose to ping were to go down, then that could cause the link to, or the route to flap over to ISP2, even though ISP1 wasn't actually in fact down. So what you can do in that scenario is create 2 IP SLA probes, 2 tracking objects, and then essentially tie those together into a third tracking object, like an aggregate tracking object, and then tie that tracking object to the default route. So what would need to happen is there would need to be no reply from either of those addresses in order to cause that third aggregate tracking object to actually go down and pull that route from the routing table. So for this example, we're just using 1 for the sake of time. So we'll say ICMP echo 8.8.8.8, source interface gig 00, say frequency 10, and then VRF WAN 1. Okay, and that's all there is to that. We just need to schedule it. So IP SLA schedule 1, start time now, life forever. And then track 1, IP SLA 1 reachability. And then in production, you'd probably want to set a delay as well for up and down. But again, this is a lab, so I'm not going to worry about that. Not too important for this. So we'll do show IP SLA summary. And it has timed out. Why did that happen? Well, the reason that happened is because the router doesn't actually know how to get to 8.8.8.8. So if we do show IP route VRF WAN 1, we don't have any way to get there. So this is where I need to make something additionally clear. I've seen this set up wrong several times, and I'm not exactly understanding why, but some might just stick a default route in there and say, okay, well, it needs the default route, and we can get to 8.8.8.8 or whatever well-known IP you choose to ping. IP SLA probe will get a response, tracking object will come up. But here's the thing, if the default route is tied to the tracking object and the IP SLA probe is tied to the default route, it's either not going to come up to begin with, or if it does, once it goes down, once ISP 1 goes down, it's not going to come back up because the default route will be pulled, track 1 will be down, and the IPSLA probe is relying on that default route to get out to 8.8.8.8. So what we need to do is we need to specifically tell the router, you need to go this way to get to this well-known address that is being probed by the IPSLA monitor. So we can do that one of two ways. We can create a static route for, in this instance, we're tracking 8.8.8.8. The only problem with that is that all traffic then that traverses this router will be forced to go that way. So even if this PC down here, say it's using 8.8.8.8 as its DNS server, it's going to take the path of ISP1 every time because there's a static that says, hey, go out this way no matter what. The cleaner way to do it is to create a route map and then essentially assign it to the router as a local policy. So that way we say, hey, any traffic originating from the router itself, ICMP traffic destined to 8.8.8.8, send it out this way. So we're going to do that, and we're going to start by creating an access list, and we'll just say, we'll call it self, because this is going to pertain to the router's self traffic. So this IPSLA monitor is going to be self traffic originating from the router itself. So we'll say IP access list extended self permit ICMP any to host 8.8.8.8 route map self match IP address self set IP next hop 172.16.1.1. Actually, set IP default VRF WAN 1 next hop 172.16.1.1. So once we applied this route map, it's going to tell the router any traffic generated from yourself, send it to, or should I say more specifically, because we created that access list, any ICMP traffic coming from yourself to host 8.8.8.8, send it this way. And we can apply this by saying IP local policy route map self. Now, as soon as we apply this, we should see this come up, at least within 10 seconds. So we'll just give that a moment. And we are back up. Do show IP route VRF WAN 1. There's our default. And now if we do show IP route VRF LAN, we should see that default route leaked into the LAN VRF, and there it is. So we have a default put in there by BGP, and it's kind of nice as well because it also tells us in parentheses which VRF it is. So we see WAN 1 right there. Okay, so the next thing is we need to create a default route for the secondary. So this is going to be the one with the higher administrative distance. And then remember, we'll have to go back into multi-protocol BGP and modify the metric, because it doesn't matter what we set it in the VRF. Once it's redistributed into BGP, that gets the metric and the administrative distance it's muddied, if you will. So, but we'll create this first and say IP route VRF WAN 2 quad 0 10.0.0.1, and we will put a we'll put an administrative distance of 10. do show IP route VRF LAN. Do you see why we need to go back into BGP and change that? Because now it automatically chose this as its preferred path. We want WAN 1 to be primary. So even though I put that metric in there, so if I do a do show run pipe section IP route, we see that this one is the default administrative distance. We just have track 1 on there because it's being tracked. This one has an AD of 10, but once we redistributed it into BGP, it still wanted to choose WAN 2, despite of this right here. And I just want to clarify something. I believe that this actually is the administrative distance and not the metric. I know I keep switching back and forth, calling it a metric and then the administrative distance, but let me just use the context-sensitive help here. Distance metric. So I'm assuming that means administrative distance. And I think I can confirm that by issuing the do show IP route VRF WAN 2 command. And there we go. Okay, so yes, that is the administrative distance, and the metric would be there. Okay, so let's go back into BGP. So we'll say router BGP1 address family. We're actually going to leave the WAN 1 VRF alone. We're just going to leave the redistribute static. We're not going to mess with the metric. Just with WAN 2. So we want to make it match the metric that we assigned it when we plugged it into the WAN 2 VRF's routing table. So we'll say address family IPv4 VRF WAN 2 redistribute static metric 10. Now if we issue the do show IP route VRF LAN command, we are back on WAN 1 for our primary. So really quick, let me just make sure I have reachability out to the internet from one of these interfaces. Nothing else is going to work because we don't have NAT set up, and obviously we're not routing. We don't have we're not running a routing protocol or anything like that to share routes between these routers. So stuff up here wouldn't be aware of the 192.168.1.0 network or anything like that. But just to make sure we have reachability out to the internet, let me see if I can ping from each of these VRFs out to the internet, sourcing it from the ISP facing interface. So I'll say do ping 1.1.1.1. We want to specify the VRF, so WAN 1 source gig 00. Okay. Something about 1.1.1.1 is always funky for some reason when I send an ICMP echo, but you can see that we do have reachability there. Okay, and we have reachability via WAN 2, although not very good. Good enough, though. Okay. All right, so let's move on to finalizing this. Configure NAT, and we're going to test and see if this works using PC1. So let's go to gig 00, and we'll say IPNAT outside, interface gig 01, IPNAT outside, interface gig 07, IPNAT inside. Okay, let's create our NAT access list. So we'll say IP access list. We'll keep it simple. IP access list standard, NAT. In production, you want to be more granular, more specific, but in this lab, I'm just going to say permit any. And since we have two different paths, and since from the inside the outside, the order of operations goes, routing and then translation, we need to create a route map and apply it to our NAT statement to say, hey, if you're going this way, translate it to this address. If you're going this way, translate it to this address. So we'll say route map NAT1 permit 10 match IP address NAT match interface gig 00, and then route map NAT2 match IP address NAT match interface gig 01. Okay, now we can go in here and say IP NAT inside source route map NAT1 interface gig 00 VRF LAN overload, and then IP NAT inside source route map NAT2 interface gig 01 VRF LAN overload. Okay, I think we have reached the end. So let's test it out. Let's go over to PC1, see if we can reach the internet. I already set the IP address on PC1 as well as the DNS server. So I'll say ping google.com. And we have reachability. Go to R1, do show IP NAT translations. You see that we're translating, so inside local is the IP address of our PC1, 192.168.1.10. Inside global, which is the IP address on this interface right here, 172.16.1.2. And then we have the IP address, whatever, when we ping Google, whatever that resolved to, which looks like it's 172.217.4.78. So we have reachability out to the internet. Let me simulate a failure of ISP1 and see if we have this working. So again, up here, I'll do a do show IP route VRF LAN just to show once again that we're going out WAN 1. And to simulate the failure, what I'll do is I'll just suspend this right here, which is going to temporarily give us a timeout. And on router 1, you should see the tracking object go down. As soon as that happens, this route is going to fail over. So we see that the IPSLA monitor just went down. Again, we'll issue the do show IP route VRF LAN command. We should see that we're now on WAN 2, which we are. Send an ICMP echo, and we are now back on the internet via ISP2. I'll unsuspend this to make sure that we switch back over. So we see that track 1 went from down to up. This route should now be changed back over to WAN 1. And it is. Ping google.com. And we're back through ISP1. And that is all. So video ran a little bit longer than I originally anticipated. I guess that's how it goes sometimes, though. So, but anyways, I really hope that you learned something from this video. I hope that it was informative. Please let me know if you have any comments. Leave them in the comment section below, or you can reach me by email at rob@rmtechcentral.com. I'd like to thank you for watching this video, and I'll see you on the next one.